Lunch and Learn today. Um, for those of you who don't know me or maybe forgotten my name is Jake Witcher, and I work here, obviously. Started the beginning of this month. Um, and I got into programming for the first time, wrote my first line of JavaScript last year, late May, early June. So I'm fairly new to the programming world in general. But a few months into that learning process, I heard about functional programming, and it really kind of piqued my interest, just sort of clicked, I guess, with how I think or how I like to work. And so I started looking into it and spent, the first few weeks, months in learning about functional programming, really just trying to digest things like pure functions, immutable data, and getting familiar with some of the methods on the array prototype in JavaScript, like filter and map and reduce, all things that were new to me, including just the concept of pure versus impure functions. But at some point, I kind of hit this roadblock of, okay, what next? Because if you look at a lot of the beginner material on functional programming, that's kind of where a lot of it stops. They're like, oh yeah, pure functions and map, filter, and reduce. Go have at it, and that's it. And they kind of leave you there. So I started doing a little more research, looking a little more deeply into what it meant to adopt functional programming as a bigger programming paradigm. And through a few different articles and books and just different resources, one of the central themes that I saw as kind of a good next step in functional programming is this idea of composure. So really the purpose of this talk is to kind of provide a good next step for somebody who's interested in functional programming, has gotten their feet wet in the basics, and is looking to progress from there. So if you're already well-versed in functional programming, this is probably going to feel a little simple, but it's meant to be kind of an overview and sort of an introductory talk on functional programming, or maybe not a 101, but a 102. And full disclaimer, as we kind of get into some of the concepts like functors and monads, this is definitely going to be a very, very shallow overview. It's going to be more like a few specific concrete examples rather than those things as a concept as a whole. But at least for me personally, it was helpful to understand them in one concrete instance before trying to step back and think of them as a broader context. So again, if you're looking to be fully versed in these things by the end of this talk, it's not going to happen. But if you're looking just to kind of get your feet wet and have an understanding of what these things are and how they tie into this idea of composure, then you're in the right place. All right, so why talk about function composition? What are the benefits to programming in this way? Well, to really illustrate this, I think it's best to actually look at some code. Now, all the code snippets in here are fairly short and simple because it's less about what's going on in the function and it's more about how we're using functions together. So here is a function with a lot going on. There's some math happening, and then there's some sort of string produced as the final output. This function as it is, it would be hard to know what the individual pieces do, why they're there, and how they relate to one another. So step one in fixing this might be to break it out into smaller functions, which is great. And that's kind of a key aspect of functional programming, is writing these sort of small, reusable snippets of code. But if we break it up into all these different functions and we write it in sort of the typical JavaScript fashion, we end up with this, which is not the most readable code. There's a lot of parentheses going on there. There's a lot of nested function calls within nested function calls. And that's why typically you wouldn't see code written in this way, because it's just not the easiest to read. This is what that same function looks like using composition. I think even you can kind of ignore the function pipe being used there. We're going to talk about that later. So for now, if you're not familiar with it, you can ignore it. But the point I wanted to make here is, even if you've never looked at code before in your life, you can probably read this and determine what it's doing and what the sequence is. I use pipe for this example because it's a top-down way of reading the code. So there is a promotion being applied, sales tax, shipping, that's being formatted. Now, I meant to mention this earlier, but I'm doing a terrible job working with currency in this code. That's because it's not real. I don't care, so don't worry about that. But this is incredibly readable. This is easy to digest what it's doing. And then the nice thing is all that information, all that implementation is sort of abstracted away into one function to handle transactions. The other nice thing about writing code this way is it's really easy to swap any one of those functions out for a different function and have a whole new function, a whole new set of functionality. So it's highly readable and it's highly reusable, which is why I think function composition is a really useful like technique in programming. But to do that, we have to have functions that can be composed. And by composing functions, what I mean is we're just like sticking functions together, like Lego pieces being stuck one on top of the other to build something bigger. So there's few attributes of composable functions, functions that can be clicked together like those Lego pieces easily. The first and perhaps an obvious one is that a composable function can't return void. The whole concept behind composing functions is that the output of one function becomes the input of the adjacent function in the list of functions. So you can't have, you know, a function that just writes to the console followed by a function expecting an input. Kind of an obvious one, but still worth mentioning. Because one thing you'll notice is that with a lot of these aspects of composable functions is they tend to be the same aspects as pure functions, with a few exceptions. Secondly, the input and output of adjacent functions have to match. So if you're not familiar with this kind of notation, the A to an A is just representing a function that takes a type A and returns a type A. That type could be anything. It could be a number, a string, a bool. So all that's saying is we have one function that takes a number, for example, and returns a number, and we're combining it with another function that takes a number and returns a number. That's good. We can do that. We cannot take two functions where the return or the output of one does not line up with the input of the other. We have to make sure the output input matches. That said, they don't all, like the first example, they don't all have to be the same input and output. We can have something that, for example, takes a Boolean and returns a number, and then another function that takes a number and returns a string. That's fine as long as the adjacent output and input matches. Then lastly, at least in terms of the ones we're going to focus on, composable function can only have one parameter, which might sound kind of limiting, but there is a way around this. I'll talk about here next. But essentially, you can't combine a subtract function there that takes two parameters and squeeze it between two single parameter functions, because add2 is going to return a single value. Subtract is going to be waiting for a second value. It's not going to work. We do have a way of dealing with this. Otherwise, function composition would be not as useful because there are a lot of times when you need a 2 and possibly even a 3 parameter function. Curry is the way we handle this. We curry functions. Now, this is sort of a hard-coded version of a curried function just to illustrate the point. But if you have a very simple add function that just takes two numbers and returns the sum, you can rewrite that in a curried format so that what the new curry add function does is it takes a number and it returns a new function that's expecting a second number that will then finally return the sum of those two numbers. So you do it one step at a time instead of all at once. Now in JavaScript, we have to sort of force this. The cool thing about functional languages like Haskell or Elm is this is baked in. Every function you write is a single parameter function. Even if you give it multiple parameters, it just always returns a new function unless it actually gets enough parameters to satisfy the entire function. So this is what curry looks like in JavaScript. This is sort of a helper function that you can use to take any function and turn it into a curried function. Now this comes from the Mostly Adequate Guide to Functional Programming, which is a great resource. It's also, you don't have to write this out yourself. There are libraries like Ramda, which is the one that I've used the most, that provide a lot of these helper functions for functional programming. And what this is doing is it's a function that takes a function as its only argument. It saves the length of that function, the arity, the number of parameters that function is expecting. So if it's a 3 parameter, it's going to be an arity of 3. And then it returns a new function, which I'm just calling underscore curry here because it's still a part of the whole curry function. This new function takes any number of arguments, 1, 2, however many you give to it, and it's going to compare the length of that array using the rest operator. It's going to bind all those arguments into an array and compare that length to the arity. And basically, what it's doing is it's checking to see, do we have all our arguments yet? If not, it's going to return a new version of that underscore curry function with the arguments it has received bound to it. And you can do this. You could have a 7-parameter function. Why, I don't know, but you could. And it's just going to keep checking to see if it has enough, and keep checking and keep checking. And then finally, once it does, it's going to go ahead and call the original function that you gave to it with the correct number of parameters. So that's kind of how it works under the hood. You really don't have to think about that, though, when you're using it. You just pass a function to curry, and it gives you a new function that can take one or more parameters at a time, or arguments at a time, until it has them all. So just to kind of illustrate that point, we can go back to our very simple add function. My, I guess, way of usually doing this is I tend to write the original function with an underscore at the beginning of the name so that the actual function I'm going to be using looks like the name I want it to look like. And the nice thing about this, and just curry in general, is now we have a highly reusable function here that, it's a 2-parameter function, but we can easily create new functions that automatically add 2 or automatically add 10. And again, this can be far more complex than basic math, but just to kind of illustrate the point, it allows us to kind of create a shell of a function and then create new functions off of it just by adding 1 or 2 parameters at a time. Something you'll notice as you get into functional programming and using libraries like Lambda is that the order and sequence of those parameters on similar functions tend to be the same. For example, like map is a function we'll see here later that gets past the callback function first, and then the array or whatever you're mapping over second. And that's intentional. It has to do with kind of the most likely way you're going to create new functions through curry. So that's really all we need to have composable functions, at least kind of from a basic point of view. We need to be able to handle multiple parameters and turn those into single parameter functions. And we just need to make sure that things piece together correctly. All right, so now we're going to take a look at compose itself, which is the function that you use to actually combine multiple functions together into a single function. I showed the pipe function earlier. I think it's a good illustration to start off with because it is top-down readable. Compose works from right to left. I'm not going to, honestly, I'm not totally sure why, other than the way pipe works in other languages is different, so we're not going to really get into that. In my opinion, pipe and compose are just a style choice in JavaScript. They don't really have a meaning beyond that, where they do in some functional languages. But at any rate, so compose is just a function that takes any number of functions as arguments. You can pass it 2, you can pass it 10, it doesn't matter. And it's going to save all those functions up in an array, and then return a new function that once it receives the initial argument, it's going to reduce through that array from right to left, applying the function to the value. So just to kind of walk through it, down at the bottom, handle transaction, we're using compose to create a new function called handle transaction. The first function, this is the one that reads bottom top, that's what the little arrow is there for, just in case. So the first function, apply promotion, is going to be the rightmost function in that array. And the argument that we pass to handle transaction, the number 10 or whatever, is going to be the accumulator for that reduce function. So the accumulator gets given to apply promotion. It does its mathy bits, returns a number. That number is your new accumulator, and that continues on until you've walked through the entire array of functions. So we've got a function that takes a number, returns a number, takes a number, returns a number, takes a number, return a string. With compose, we don't really need to think about those steps anymore. We just need to look at handle transaction and say, this is a new function that just takes a number and returns a string. It's a way of having those implementation details where they're easy to swap out and change, but also being able to ignore them and just think of the new function as a function that does a very simple one-to-one input-output. All right, so here's pipe. The only difference is that it just uses reduce rather than reduce right. So it moves from left to right through the array instead of right to left. There are other ways to write these functions, but I think this is the simplest, the easiest to sort of see what's going on. All right, so, and then just to kind of illustrate the distinction there, the one on the left is reading from bottom to top, the one on the right, top to bottom. All right, so this is how curry and compose sort of interact with one another. Again, we have two very simple, math functions there, add 2, add 5. Then we have that subtract function again that was causing problems because it's a 2-parameter function. by creating a curried version of subtract and giving it the first parameter there, that subtract 4 is now the equivalent of just a simple lambda of y to y minus 4. So it is now a one parameter function, and that pipeline is clear. And that's sort of how I think about functions in function composition, as sort of each individual function as this piece of metal pipe. And if you line them up correctly, if their inputs and outputs match, and you give them the right input to begin with, it's like rolling a golf ball through those pipes, and it just passes straight through and out the other end with the data transformation that you were looking for. And this is a way to be able to do that and still have 2, 3, 4 parameter functions. All right, so that's all well and good for very kind of like simple examples. And there actually is still a lot you can do just with that information. And if this stuff is new, I would highly recommend creating a new project, importing the Lambda library, and playing around just with curry and compose and pipe. And I think once you get started with those, you'll start to see how a lot of other functions in the Lambda library just help you do the same thing. For example, there's a function called flip that just takes the parameters and flips them. So if you need to compose, but you actually need the first parameter to be the one that gets passed through the compose functions, and you need the second one to be the one that you feed it in advance, then you can flip the parameters in that way. And there's a lot like that just help you adjust the way your functions work, so you can get those pipes lined up nice and neat and run the input-output straight through. But when you run into the case of invalid arguments, there are, of course, ways to handle this. And let's just take a look at what happens when handle transaction, so in this case, I've actually split it up into 2 different functions. I like to compose functions by what they do. So calculate total does all the mathy stuff, and construct message does all the string creation stuff. And so I'm actually taking 2 functions that were composed of other functions and then composing them into a new function. And you can do this on and on and on. Just build, build, build. Again, just like Legos. But right now, the way it is, if I give it a number, I get the output that I would expect. Like, that's the correct output given that input. If I give it the Boolean value true, I get $5.74. So if you are true, you cost $5.70. I don't know. That's because lovely JavaScript coerces the Boolean value true to a 1 and then runs our math like everything's fine. JavaScript has your back. It just doesn't know what it's doing some of the time. Like, yeah, you got this. It's going to work. I'm going to make sure it works. And you get the wrong answer. And then, of course, you pass it a string, and it's still happy to run this function with a string and give you an output that's totally useless. This is probably not new stuff if you've been working with JavaScript. And one way of handling this would be doing some sort of validation before you pass anything to the function. If it's this, then do that, something along those lines. Well, functional programming is sort of a built-in way to handle this so that we can continue to compose functions and not really care about what our data is going in, and also to have an incredibly predictable output, whether we get the right data or not. We know exactly what's coming out the back end without any testing really or anything. So is there a way to preserve? Yes. Yes, there is a way to preserve this composition and get the output that we want. But before I really describe how that works, especially if some of this is very new, I want to talk about arrays, because a lot of the same ways that we work with arrays work with functors, which is what we're going to move into here in a minute. So if you've got an array, it helps to kind of think of arrays differently, almost as if you've never worked with them before. And think of an array as this special context, the special container, the special environment. And everything that is inside of it is safely inside of it, but it's also inaccessible from the outside. So we can't just say array times 2 and hope that that's going to give us some valid output. That's if we wanted to double every value in that array. And that's because our operator, the multiplication symbol there, it can't access the values in that array. They're safe, but they're also stuck. We have no way of getting to them. Or actually we do, and that's what the map method is for. Map, you want to think of map as this special function that gives you access to this separate context so that you can do stuff to it. And I imagine most of you could probably write a function that does what map does without calling map. You don't have to because map is there. And honestly, you don't even have to think about the implementation. You don't care. You just give it a function because you trust that it already knows what to do with that function in its given context of an array. It knows to apply it to every value of an array. Again, this is really kind of, in one sense, this is maybe simple stuff, but I think as you see how this plays into using functors and then monads, it becomes really important to think of it in this way. So map is this special function that lets you reach inside an array, inside of this separate context, and transform what's stored inside of there that otherwise is inaccessible to you. In functional programming, we create sort of like a helper function. It's sort of a dumb map is how I think of it. And it's a function that, that just takes a function, and then I've created sort of a hard-coded curried version here. I'll show you a different version later where we actually use curry. But it takes a function, and then it returns a function that's ready for an array. And when it gets an array, it just uses the native map method on that array and passes it the function. Seems pointless. And again, if you haven't kind of seen some of the stuff, I've noticed a lot of things in functional programming look pointless until you see where it goes. So just stay with me for a moment. That's also why I call it the dumb map function, because it literally just gives it to the map method on and doesn't actually do anything with it itself. So this is what our functions kind of normally look like. A typical A input to B output. The big orange square there is our input on the left-hand side. Orange square on the right is our output. The blue rectangle in the middle is our function. With that helper map function, what we end up with is a transformed A to B function that now, instead of taking a value as input, it takes an array as an input, and it returns an array as output. So we've transformed the shape of the pipe, so to speak, of that function, so that it can now take a different shaped input. In this case, it happens to be the shape of an array, so to speak. And then just kind of illustrate how that plays out, we can give it our doubling function, create a new function called mapDouble, pass it to the array. These two things are doing the exact same thing. Now, this is sort of what it looks like when we compose with map. So we can now pass the really well-named function doMaths an array. And again, this is not interesting functions going on here, but the point is it's going to then go, the first map is going to pass that subtract function to our array. The array has the method on it that knows how to handle it, so it's going to subtract to everything in the array. The next step, that second map is going to pass the function double, go through the array double everything, and on and on. Now, this isn't necessarily needed. I just find this really interesting. You can write it like this, or you can actually compose those functions together first and then map over all of them. It's an element of associativity in functional programming where mapping over functions independently is the same as composing those functions together and then mapping over them all at once. And so it just gives you some flexibility on how you structure things. And again, I think later we'll see sort of how that gets utilized. All right, so we can do this with arrays, which is something I think everybody's pretty familiar with if you're, especially if you work with JavaScript or most programming languages. And we can do this with other types of context containers that we can imagine, so long as they have a map method on them. Like that's really all we need to do this exact same thing. So this is the same map method as before, only this one is a curried version where we're just showing the two parameters all at once and then using curry to create one that takes one parameter at a time. Only instead of referring to it as array, I'm calling it a functor now, because now it does more than just map arrays. It maps over all kinds of contexts that we can think of. So instead of an array to an array, we now have something that can take a functor of any kind to a functor of any kind. So let's take a look at our first functor. And again, an array essentially is a functor. So if you kind of understand an array, really what we're going to look at now is another type of functor, but rather than holding a set of values, it's going to hold a single value. So it's a little different in JavaScript because of the way you have to write this, and there are all sorts of, again, there are libraries that can do this for you, so you don't have to do it yourself. But I think this simplified version sort of helps illustrate the point. So the first functor we're going to be looking with is a maybe number functor. Now, if you look into functional programming materials, a lot of times the first example they give is the maybe functor or the maybe monad. I changed it up a little bit just so that it fits with the context of what we're talking about. We have a set of functions that need a number, so we're going to create a functor that checks and makes sure we have a number as an input. And again, JavaScript doesn't let us map this exactly the way you would from a functional language. And I'm trying to treat this class almost like a static class. We're never going to instantiate maybe number. Instead, we're going to use the static method of on it. And the names of these methods are just kind of like traditional functional programming method names in JavaScript. Sometimes they're different in other languages, but I didn't choose them. They're just there. And that static method of checks to see if the value it receives is a number first. And if it is, it's going to return something called just number. And if it's not, it's going to return something called nothing. There are going to be two other classes that we'll look at here. And the three combined, you want to think of them all as a single functor. And in a language like Haskell, they would be a single data type. And so just to kind of illustrate that point, you want to think of all of this as like the maybe number functor. And in Haskell, they would be. And that bottom left is an example of what this data type looks like in Haskell. It's a single data type of maybe A being anything. You can give it a string, a number, or whatever. And it's either going to be a just A or a nothing. It's called a sum type. You never concretely construct a maybe in Haskell. You only construct a just or a nothing. And in an attempt to recreate that in JavaScript, we have a maybe class that's acting almost like a static class that's never going to be instantiated, but it will either instantiate a just number functor or a nothing. So let's take a look at what those look like and kind of see how this all ties together with function composition. So just number is somewhat similar. This time we do have a constructor, and rather than directly calling a new just number, we use the static method of again to create a new just number. Again, these are kind of, I'm sure there's reasons behind it, but this is kind of like the typical way it's done in functional programming in JavaScript. But then it has a map method on it as well. And this map method, much like the map method on array, knows what to do for its unique context to handle a function correctly. So this map method takes a function, it applies the function to the value held by the just number functor, and then it returns a new just number with that transformed value as its value on the value property there that's created by the constructor. So it looks very similar to what we've seen before, right? Only instead of an array, we have a functor, and our dummy map helper function from before, because it doesn't care what kind of functor it gets and what kind of functor it passes a function to, all it cares is that functor has a map method on it. And that functor knows what to do with the value it's given with that map method. Our dummy function doesn't care, it just transforms any function into something that's ready to receive a functor and return a functor. The nothing class is what we get when we don't get a number in this case. So maybe number is going to check. If it's not a number, it's going to wrap it up in a nothing functor instead, using that static of method. But I want you to take note of the map method on this one. It completely ignores the function it receives as input, and it just returns a new nothing. That's really important in terms of how all of this works. They're different contexts. They each have their own map method, and their own map method handles things correctly for that context. So the one will actually apply the function to the value. The other literally does nothing and just returns a new version of itself. And this is what, how you kind of illustrate nothing using the same idea. All right. So we're going to take a look at this in the actual application we've been sort of working with here. Just as a kind of reference point, these were the functions. We're going to break them up into two different functions called calculate total, create message. Compose those together into their two new functions. And then now this is what our handle transaction is going to look like. It's no longer just calculate total and construct message. Instead, it starts with the maybe number.of, which is that static method on maybe number that either instantiates a new just number or a new nothing. So we give it an input, we give it the value 15. It's going to check if it's a number. It is a number, so it's going to wrap it up in that justNumber class, that justNumber object, which has its own map method on it. Its map method knows what to do. So when our dummy map here gets past that second parameter of that justNumber functor, it's going to go ahead and hand it over the calculate total function. It's going to run that over the value hidden inside that justNumber, and it's going to return a new justNumber with the results of that calculation, pass it on up to the next map function, and repeat the process. However, if the maybe number static method of realizes that what it received was not a number, it's some other kind of value, any other kind of value, it's going to return a nothing. That nothing has a map method on it that just does nothing, which means we can continue to just throw values down this pipe, and it knows how to handle them regardless of what they are, and we get a very predictable result at the end every single time. So just as a reminder, this is what things looked like before when we passed those different value types to the handle transaction function. This is what it looks like now. We get a 15. We're going to receive a just number of the actual output we're expecting. For everything else, we're just going to get a nothing. Now, I gave the value on nothing, the string nothing. You could put null, you could put undefined, you could do whatever, really. But the point is, like, no matter what we feed this function now, we're guaranteed to get the result we expect. We're either going to get a nothing or we're going to get the total that we wanted. And this is a lot of code to get that to happen for just one little function. But this maybe number functor across an entire application is saving you all of these data validation, if then else type statements. So it's a way to neatly kind of wrap all of that up, and it also is a way to really have a predictable output every single time. So what if we have more than one possible source of invalid data? It's not just the initial input, but let's say there's some sort of file that needs to be read along that stream of functions, or there's an API call that needs to be made, and we're not sure if that file we're reading or that API call is actually going to return us the value we're expecting. This is just a made-up function. You really don't need to worry too much about it. All you need to know is it's in the code to simulate that kind of unpredictable, are we going to get a number back, are we not? And the result, the important part there is the return maybe number.of. Like the important part is that it doesn't just return the result of the calculation, it returns the result wrapped in either a just or a nothing. Again, this is terrible code, it's just here for illustration. So if we were to try to use that new apply sales tax function and compose it the way we did before, we'd run into a problem. Because now apply sales tax doesn't just return a value, a number, it returns a functor. And apply shipping is expecting a value, and that's a problem. Now we can solve it at this level pretty simply by just mapping over apply shipping. However, on our main function, handle transaction, it's not expecting calculate total to return a functor. It's expecting it to function like this, to just be a simple input-output function. Our new calculate total, though, looks like this, which is a problem because if we run it through that run a value through that handle transaction code, using just map as before, it's going to break actually when it gets to the construct message. So if we just comment that out and don't use it for a minute, then this is what we're going to get returned instead. We're going to have a functor wrapped inside a functor. And that's not really helpful because now we have multiple layers to dig down into to get our value. And if you can imagine, if there's multiple sources over the pipeline of a bit of data transformation, you're going to end up with just layers and layers and layers, and you're going to have to map to dig down into the initial layer. So this is where the monad comes into play. And again, this idea of like a functor and a monad is much broader than this, but I think this is a very nice, concrete, good starting point illustration of these ideas and the kinds of functionalities that they have. So in this case, initially it looks very similar to what we had before. This is all the same. The new things that make it a monad is that it has a join method, which simply returns the value that it's storing. And it has a chain method that gives the function to map and then passes the result of that to join. So what that means is, remember that function looks like this. the one that we're giving to chain, which means that when it passes it to map, map is expecting to return whatever it gets wrapped in a functor. So we've given map a function that returns a functor, and then map is going to wrap that inside another layer. So our function returns kind of layer 1 functor, and then map returns it layer 2. Join pulls out that internal layer so that all we get on the back end is the one in the middle. So that just means if that function given to chain produces a nothing, even though that map is going to wrap that nothing in a just number, the join is going to pull out the nothing from inside, and that's what it's going to receive on the back end. Or if it's a just and a just, we're going to end up with a single layer instead of multiple layers. Which means now this is kind of what chain looks like. It can take a just number monad. It can transform a function. That A to MB is just kind of a functional programming way of saying something that takes an A and returns a monad of B. And still produce the exact same output that all of our other functions are producing, so that once again, everything in that pipeline is the same. It's all getting the same input. It's all sending out the same output. So this is what our final kind of handle transaction would look like. And once again, maybe number is creating either a just number or a nothing functor. Chain is accessing, it didn't show how that works, but it's essentially exactly the same as map. It's just a helper function that accesses the native chain method on a functor, whatever that chain method is meant to do. The other thing we didn't look at is the nothing monad. That nothing monad has a chain method on it as well, and all it does is return any nothing. Again, so that way, no matter what we pass through, we either end up with a nothing on the end as the output, or we end up with a single layered monad with the value inside of it that we can easily access. And then once chain sends through a single monad with a value inside, map can do its normal thing as if nothing has changed, nothing has happened. All right, so in terms of next steps, if this is interesting to you, if this is something you would like to get more into and learn more about, there are a few resources that I highly recommend for doing so. The first is just the Ramda library itself. I would recommend just getting into that, playing around with it, and trying some of the different functions there. The Mostly Adequate Guide to Functional Programming by Brian Lonsdorf is excellent, as is Composing Software by Eric Elliott, which is, there is a book, but there's also a series of articles. And if you go to the GitHub repo there at the bottom, links to all of this stuff is on the README in that repo, as well as all of the examples. I shouldn't say all, but like the main ones. So it's got the monads in there, it has the helper functions, and it has the handle transaction as it's done in the functor example, and the handle transaction as it's done in the monad example. Haskell book, I know it's not JavaScript related. So the first two, Mostly Adequate and Composing Software, are about JavaScript. So that's nice if you're working in JavaScript and using these techniques. Haskell book obviously is not, it's about Haskell, but I would still highly recommend looking at a true functional language to learn some of these concepts, because it just helps to understand where those concepts are coming from, because the way they're implemented in JavaScript is a little wonky, not quite accurately representing what's really going on. So it's just helpful to see those concepts in a true function. All right, go forth and compose all the things.